All right, so this short video is going to introduce the sort of the formal idea of a limit, which corresponds to section 2.2 of our calculus textbook, Briggs and Cochrane. So I want you to pause, copy this down, and then I'll start talking. All right, so limits are going to be of fundamental importance for calculus, and we're going to sort of introduce and calculate a few in a very basic way today. So we're going to define the limit of a function at a particular x value, which I'm going to call x equals a. All right, we need, first off, the function f has to be defined for all x values near x equals a, right? Near it. What's happening at a? I won't care, okay? But suppose the function f is defined for all x near a, except possibly at a. So my function might not even be defined at this value, this input a. All right, well, if f of x, our outputs, are arbitrarily close to a number L, which means as close to L as we could possibly like, for all x, for all inputs sufficiently close to a, but I'm not going to plug in a, then we write the limit as x approaches a of f of x is equal to L. Okay, so we write the limit of, we say the limit of f of x as x approaches a equals L. A little bit, have some commas in there. Okay. So one more time, the limit of the function equals L as x approaches a if our outputs get as close to L as we possibly could desire as our inputs get pretty close to a, right? Now note, the actual value of the function at x equals a doesn't impact the limit whatsoever, as what I'm hoping the next example will show us, right? It's a very complicated definition, to be honest, but let's look at a few examples and see if that helps. All right, so why don't you copy this thing down carefully. Note that there's a hole in the graph at x equals 2 and at x equals 3, okay? All right, so pause, copy, press play. We are going to learn to calculate limits two ways today. One is via looking at a graph, and the other way is via building a table, which is what the next example will show. All right, well, here is the graph of f. It looks like a line followed by another line, couple of holes poked in it, and one dot plotted below a hole, okay? And we're going to calculate a few limits, and we're going to calculate the function at a few points. So first off, what is the limit as x approaches 1 of f of x? All right, well, my answer is what outputs is my function getting really, really close to as my inputs get really, really close to 1, okay? So as my inputs get really, really close to 1, it looks like the y values I'm getting close to are all right around that number 5. So as x's get really, really close to 1, their corresponding outputs look like they're getting really, really close to 5, okay? So I would say, hey, this limit is equal to 5. Remember, the limit is the output value that we're getting really, really close to. All right, now, what happens to be f of 1 itself? Now, the limit doesn't care what's happening at x equals 1, but just for curiosity, what's happening to the function at 1? So if my input is equal to 1, my output is equal to 5. So in this case, the limit and the limit as x approaches 1 and the value of the function at 1 are both 5. Does not have to be that way. Let's see. All right, now let's look at the limit as x approaches 2 of the function. So as my x values get really, really close to 2, it looks like the outputs are getting really, really close to this hole, which is at 10. So inputs close to 2 are causing outputs really close to 10. So I would say the limit as x approaches 2 of my function is 10, okay? All right, now again, the limit doesn't care what's happening at 2. But if I wish to know what is f of 2, well, let's see, at 2, it looks like I plotted the point right here with an output of 5. So f of 2 is equal to 5, okay? So sometimes the limit as I approach a is equal to the function's output at a. Sometimes it is not. All right, let's do one more. Let's look at what happens, the limit as x gets close to 3 of f of x. So as my x values are getting really, really close to 3, it looks like the y values are really getting close to that open dot, which is at a y value of 15. So I would say this limit is equal to 15. Okay. And again, what's happening at 3 is irrelevant for the limit. But if you wish to know, let's try and calculate f of 3. So if I try and plot the point at x equals 3, I see there is no dot anywhere to plot, which must mean this f of 3 is undefined. Okay. We also say sometimes does not exist. Does not exist. All right, so we've seen 3 separate things. Sometimes the function is in agreement with the limit, sometimes it's not, and sometimes the function doesn't even exist at the x value we're taking the limit at. Okay, so the limit truly doesn't care what's happening to the function at that x value a, just what's happening as we get close to that x value a. All right, let's do a table example now. All right. So why don't you copy this down, pause it, copy, press play. All right, so I've got a somewhat complicated function, the square root of x minus 1. So that minus 1 is not under the square root, like it's the square root of x and then subtract 1 divided by x minus 1. And I'd like to estimate the limit as x approaches 1 of this function. Okay, so first off, please note if I try to plug in, and then I'm building a table of values now, and I'm going to crank out the outputs. If I try and plug in x equals 1, I get a 0 in the denominator, which is undefined. So I'm going to say at x equals 1, this function does not exist. Okay. All right. So a limit tells me plug in inputs really, really close to 1. So here are some inputs, some x values really close to 1. 0.9 is close to 1. 0.99 is even closer. 0.999 is even closer. And 0.9999 is even closer. And I could continue this process, right? So that's sort of less than 1, but close to 1. Here are things greater than 1, but close to 1. X equals 1.1, 1.01, 1.001, 1.0001. These x values got to go really, really close to x equals 1. And all I'm going to do is I'm going to take each x value, plug it into this function, and crank out my answer. Now, trust me, I used a calculator. Here's the answers I'm getting. I get 0.51317. I get 0.50126. I think I rounded it to the 5th decimal spot. And then I get 0.50013, 0.50013, and then I get 0.5000, 0.50013. I guess that one I went to 6 decimal places. All right, and then from the other side, when I plugged x equals 1.1 into my function, I got an output of 0.48809. When I plugged in 1.01, I got 0.49876. When I plugged in 1.001, I got 0.49985. And when I plugged in 1.0001, I got 0.4999875. Okay. All right. So let's say you can check me if you like. All right. So let's say you spent the time, you cranked that out, you built an Excel spreadsheet, shoosh, out we come. The limit is looking for what are my y values approaching as my x values approach 1. So here you see the x values getting closer and closer to 1, from below 1 and from above 1. And so the question is, what are these y values approaching as I get closer and closer, as my x values get closer and closer to 1? Well, and it looks like, in my mind, it looks like they're getting a really, really close to 0.5 from either side, right? These outputs are getting closer and closer to 0.5. Here they're getting closer from above 0.5, and here they're just underneath 0.5, but getting closer and closer to it. So I would guess these Y values are really, starting to collapse on the number 0.5. So I would estimate via the table that this limit as x approaches 1 of f of x is equal to 0.5. All right? The actual value of f at 1, not even defined, doesn't exist. But the limit we can calculate via this table. We'll talk about how much of a table you ought to build for these in class.